that we have broken down our videos into secant. Now let's do tangent. So let's do examples of videos of substitutions that involve the tangent. So you're gonna have, those are the easiest to identify. So this video may not be as long, but you will have plus. So whenever you have the sum of squares, you know that's going to be a tangent. So that one is the easiest. So you're gonna have your triangle. So let's go ahead and draw our triangle. And so here you're gonna have that these two are going to be the sides of the triangle. They're not going to be the hypotenuse. So you've got to choose. Usually we put the x term here and the other one, the constant term, on the other. The reason for it is because then you have x divided by 1, opposite over adjacent, being the tangent, so it gives you your substitution right away. If you were to put the x down here, then you would end up with a cotangent. As before, we do not want to do that because then we end up with the negative cosecant squared, and you're throwing in an extra negative there that is not necessary, so that's the only reason for it. Would it work? Of course it would work, and you would be able to compute your integral anyways, but it's traditional to write just x here in the opposite and then get the tangent substitution. Anyway, so here we have, again, x squared plus 1 squared is equal to this quantity squared, which we can call c. So x squared plus 1 equals c squared. So when you take square root on both sides, the positive square root, you get x squared plus 1. And so with that, we can go ahead and write that x squared plus 1 over 1 here is going to be hypotenuse over adjacent. Now, adjacent over hypotenuse is cosine, so hypotenuse over, sorry, I said adjacent over hypotenuse is cosine, so hypotenuse over adjacent is the secant. So you have secant. Alright, so the only thing I'm missing here is my dx, which is going to be the derivative of the tangent, which is secant squared, dx. Alright, so d theta. I did that in the previous video as well. So we're going to substitute the dx with that. I'm going to substitute the square root of x squared with that. So what do we get in the end? We get the integral of secant squared d theta over the square root, which is just the secant. One secant cancels, and you just get the integral of the secant, which we know is the natural log of the absolute value of the secant plus tangent plus c. Now it's just a matter of substituting in what the secant is and what the tangent is. So natural log, now secant, I have that is the square root of x squared plus 1. And the tangent is just x. And just like that, you get your integral. Alright, let's do another one. So for example, now let's throw in an extra, maybe an x squared over here. And let's put a different squared. So x squared plus, whoops, that squared looked a little too excited there. Plus, and let's do 25, another square. Of course, this doesn't have to be a perfect square. The only problem is that then you'll have to take the square root in your triangle, and I don't like writing extra square roots, so my problems usually don't involve it, but it doesn't mean that it has to be a perfect square. Say for a second, let's say that I had a 2 instead of a 25, then I would grab this one to be x, and this would be the square root of 2. Because remember that this is the square already, so you have to do a square root. Let's not do that. Let's put a 25, and let's do the square root of 25, which is much nicer. So it's a 5. And here, as we discussed before, is going to be your x squared plus 25. So that's our triangle right there. That's just using your picking the x here, then the 5, and then this is the Pythagorean theorem. So just writing it as x squared plus 5 squared is equal to c squared, and then taking square root on both sides. That's where that comes from. So Now I do x over 5 is going to be equal to the tangent. That's opposite over adjacent. So it's going to be the tangent. Then I do the square root of x squared. Why? Because that's what I need here, so might as well. By the way, it is in the denominator, so you could also do 5 over x squared plus 25 and write it as the cosine. But I find that that causes trouble. But again, you could do that. You know what? Let me show you how you can do it. Just for today. So if you do adjacent over hypotenuse, it's going to be the cosine of the angle. Usually we keep it with secant and tangent because, well, that's going to make things easier. In any case, so I'm going to write x as 5 tangent. I may have to turn it back to secant, but just want to show you that you could do it that way as well. In any case, so here I take my derivative, so I get secant squared d theta. And so my integral becomes, I'm going to substitute this x squared with 25 tangent squared, just squaring the 5 tangent. So 25 tangent square of theta. Now I need the dx. I didn't want to do that. I want to do this one. My dx is going to go in here. And I put it as 5 secant squared. Yeah, I already see the annoying thing that I did to myself, but that's okay. We're gonna keep going along. Now the thing is, I'm gonna have to grab my 1 over the square root of x squared plus 25. Yeah, that's ugly. And I'm gonna write as cosine over 5. So I'm gonna have to multiply it here over 5, and I still need a cosine, so I'll have to move this d theta. Now it's going to be okay, but it would have been much easier just to write the square root of x as the secant of theta over 5. In any case, times 5 times the secant. I was just checking if I had done it correctly. Everything is correct. All right, so here the cosine will cancel a secant, because secant times cosine is 1, because they're multiplicative inverses or reciprocals of one another. I again don't recommend you do what I did. I would just recommend to write, and let me say what I should have written. So x squared plus 25 equals 5 secant of theta. So just saying this one divided by this one is going to be your secant. And then you substitute in here with a secant, which cancels again. The 5 again cancels the 5. So everything works the exact same. I just feel like the cosine, it was unnecessary. Again, as I said, when I was doing it, I just wanted to show you that you could do it that way anyways. But I recommend that when you're solving your problems, you do it with the secant. The secant and the tangent play nicely together in a sense. And we end up with tangent square theta secant here. So again, this is one of those that you will have to do integration by parts. In the previous video, we did that. And we actually solved this exact same integral. So if I remember correctly, we'll check. But we got the natural log of the secant plus tangent. And then I believe it was plus secant tangent. Let me verify this result before I move on. See if my memory is serving me well. Well, good thing I checked because this was a negative. But hey, not too bad. Alright, so we computed that integral in the previous video, so you can go back and check it. It was integration by parts, and we had to play the game where you add and subtract on both sides. You add the integral on both sides to get your result. Nonetheless, I went in detail on that one, so you can check that video. But now the question here is to evaluate or to substitute in what each one of them is. Now, secant, as I have here, if I divide by 5 on both sides, so let's do divided by 5, have what the secant is, and the tangent, I have it over here. So I'm going to substitute those two in. So I would get, it's probably better to write secant tangent minus. So secant tangent is going to be x over 5, and then square root of x squared plus 25 over 5. Let me put that 5 times 5 in the denominator as 1/25th, and I'm going to copy the x, and I'm going to copy that square root of x squared plus 25. That's just dividing x over 5 and then x squared plus 25 minus 5. Minus the natural log of the secant, which we said was square root of x squared plus 25 over 5. And then plus the tangent, which is x over 5. Let's put the plus c out here. And now remember that we can distribute this and write the 25 and the 25 cancel. We get 1/2 of x square root of x squared plus 25 minus the natural log of, and remember the common factor 1/5. I did this in the previous video, so if you haven't seen it, I took a common factor. So here I can take a common factor 1/5, and then I can separate the logarithm as logarithm of 1/5 plus the logarithm of just the numerators, because now I just get the numerators. But you have to remember now that that natural log of 1/2 I can involve into this, or incorporate into this constant, so I can leave it just as the terms without the 1/5. That's the upshot of that, which means that I can simplify my equation, provided, of course, that I don't forget my 25 halves. That would be nice. So we get 25 halves of the natural log of x square root of x squared plus 25 plus x. And that gives me my integral right there. All right, so let's do one last one for the road. And let's make it one of those where you have to complete squares. So let's do, I don't know, let's do 1 over, I'm probably going to get myself into trouble here, but that's okay. It's always fun to do. 3/2. I don't know, we'll figure it out. Let's put the dx up here. All right, so, well, let's draw our triangle just as we did before. So our triangle here is going to be, oh, wait a second, I have a 4x. I don't have a 4. So you see, that's the problem. So what do? Well, now, if you watch the previous video, you know you're going to complete the square. So we're going to go ahead and grab this x squared plus 4x plus something minus something, everything to the 3/2. So what is that something? Well, you grab this 4, divided by 2 is 2, and then you square it. So it's going to be a 4, because 2 squared is 4, and that's what I need, because now this is a perfect square. This is going to be the square root of dx over x plus 2 squared minus 4 to the 3/2. And so now, oh, that one, I failed there. I had to give you something else, so it would end up with a plus. Oh, that was a bad mistake. Well, let's force it. Change your problem. So plus 8, and that is your problem. Let's assume the problem had a plus 8, because, well, what I did is correct. I just want to end up with a plus, so I can do a tangent substitution. Otherwise, I'll end up with a secant substitution, which is what we did in the previous video. So let's go ahead and let me rewrite the problem with that plus. All right, that was the problem. That's the problem of writing your problems on the fly, but here it is. So let's say that it had a plus 8. The only reason I added that is because I don't want a secant substitution. The video is called Trigonometric Substitutions that involve a tangent. So, well, let's stick to it. So anyway, so I want to pick my opposite to be x plus 2. So the term that has the x, that's going to go there. The reason for that is, well, because again, I want to end up with a 2 here, and whenever I write my tangent is going to be x plus 2 over 2. If I put my x plus 2 over here, then I end up with a cotangent. That's not what I want. Again, since it's plus, you know that your hypotenuse is over here. the hypotenuse will be the square root of this function that is inside. But that just boils down to, you can FOIL it out and write it as x squared plus 4x plus 8. That's going to be your hypotenuse right there. All right, so now we do our substitution. X plus 2, or our triangle, our tangent. X plus 2 over 2 is going to be the tangent. So if you multiply both sides times 2, you get 2 times the tangent of the angle. That's going to be x plus 2. And now this, if you divide it by 2, that's square root. You would be doing hypotenuse over adjacent. Hypotenuse over adjacent, as we have discussed, is going to be the secant. So over 2 equals secant. Let me multiply the 2 on this side. A little bit nicer that way. Ooh, what is this? Get out of the way. There. So we get that, and then here I can take my derivative on this. So I get dx is 2 secant squared of theta d theta. All right, so what all do I need? Let's take a look. I need, this is gonna go here. Now, there's a little bit of a problem here, but it's no big deal. You see what I have there? I have a 1/2 power here. So this square root is a 1/2. Well, what I can do, if I cube it, then I get a 3/2, the power of 3/2. So what I have here is really the cube of this 2 times the secant. So this becomes 2 secant squared. That's my dx. And now for the green one, I'm going to put a cube there. So it's going to be 8. That's the 2 cubed. And then secant cubed. Now it worked out really, really, really nice. Because now I'm going to have the cube. Is gonna, so 2 of these are going to cancel 2 of these. I'm going to be left with 1. And the 2 8 is going to be 1/4. So I'm going to have 1/4 of the reciprocal of the secant, also known as the cosine. And then I just get 1/4 of the sine plus c. Now 1/4 for the sine. What is the sine? Look at your triangle. Sine is going to be opposite over hypotenuse. So opposite is x plus 2. Hypotenuse is that square root of x squared plus 4x plus 8. Now, as I don't like the 1/4 like that 4 thrown around alone by itself, let's put it there. It came out too close to the, we can give ourselves some room. There you go, plus e. And that's your integral. All right, so the tangents I think are a little bit easier. But so anyway, so that's gonna wrap up the video, and I'm gonna create another video for trigonometric substitutions that involve the sine. All right, so that's that for this one. So I'll see you in the next one.